Lesson on resistance and Ohm's law. Last lesson was on voltage and current, so we went through what's meant by voltage and current, what are they measured in, and how would you actually go about measuring them. So really quick recap, remember voltage is a measure of the energy given to each coulomb of charge. So it's the kind of push that drives our charge carriers, which are electrons around the circuit. It's measured in volts, and we can measure it with a voltmeter. Remember, voltmeters get connected in parallel, so they go kind of across the component. Voltage doesn't flow through something, we're taking a measure of the potential difference of electrical energy. Current is the flow, so that's the flow of electrons, in this case, talking about electrons carrying a charge around a circuit. It's measured in amps, and we can measure it with an ammeter, which gets placed within the circuit because the current has to flow through the ammeter so it can take a measurement of it as it passes through. So today we're going to look at resistance. I mentioned resistance last time, quite briefly, but we're going to get a proper definition for it, what it's measured in, how you would measure resistance, and then find the relationship between voltage, current, and resistance, and that's what's mentioned here, and say Ohm's law. So we're going to find out what is Ohm's law and how are these three things connected. Okay, so definition for resistance then, and you can copy this down if you're wanting, if you're making notes from in any booklets or anything. I've got resistance is the opposition to current flow. So think if you resist something, you're kind of fighting against it. So electrical resistance is what's opposing our flow of current. So it's what's kind of making it more difficult for our electrons to get around the circuit. So a couple of things to point out. Resistance is measured in ohms, and the symbol for ohms is this one here, it's the omega sign. And also that all components have resistance. Okay, for some components that resistance is always going to be pretty constant. For things, how much resistance they have can change. So for instance, and I'll get into this more later on, if you think of like a light bulb, a normal kind of filament lamp, as that heats up, it kind of changes the way the atoms behave, and as it gets hotter, they actually kind of provide more resistance against the electrons that are trying to flow. So that doesn't have a constant resistance, but lots of things do. But all components that you're going to come across, we're going to look at motors, fans, everything that you're going to see in this course will have resistance. Even the wires in your circuit have a resistance. Normally that's pretty small. Normally we can ignore it for our calculations, but it's good to be aware that they do have resistance. Some components, their sole purpose is to provide resistance, so to help us control the current by providing that opposition to it. So these things are called resistors. So that's the purpose of a resistor. So other things do have resistance, but we can get these things called resistors. They're designed to have resistance so that we know what that resistance is, and we can control the current in the circuit. So this is the symbol for a resistor. Quite often you'll see a number on or maybe above, depending on the kind of space in the diagram, the resistor, and that'll tell you the value of the resistor. It just means how much resistance is providing. So 50 ohms, 10 kilo ohms, so that would be 10,000 ohms, 100 ohms, just as some examples. You do get things called variable resistors as well, and just as the name suggests, that's a resistor where you can vary its resistance, so you can change it. We don't always want to have the same opposition to the current because we don't always want to have the same current. Sometimes you might want to change the current, and that's what a variable resistor would allow you to do. Okay, so looking at the relationship between voltage, current, and resistance then. So I just kind of want to talk through some scenarios and see if you can understand what I'm saying would happen if you did have a fixed resistance. What would that mean about voltage and current if they were changing? If you did have a fixed current, if you did have a fixed voltage, and hopefully that helped you see where the formula comes from and how the formula makes sense kind of mathematically. Here I've just got a link to the FET website that I showed you how to get to last time. So I've actually already got it open. So if I just actually go down here, or maybe not. Okay, so I already have it open, so just to save time, I I'll go to this one here, the one I made earlier. So you should know how to get into this website and how to set up this circuit. If you don't, if you go back and look at my first Loom, that'll show you how to do that. But I've just set up a battery, I've got some wires, and I've got a resistor. You see, this is a picture of what a resistor can look like in real life. There's kind of color code that you can read to say what the value of the resistor is. Just so you're aware, we don't need to be able to do that, but it's just quite interesting. So I've set this to be 2 ohms. And if I increase the resistance, we can see from this diagram what that's going to do to the current. So if we think about it, what would increasing the resistance do? Well, we're increasing, we're having a bigger opposition. There's more kind of fighting against that current getting around the circuit. We've still got a fixed 12-volt battery, so they're still getting the same push, there's still the same drive to go around it. So hopefully you can kind of anticipate this, that as we increase the resistance, you're going to decrease the current. Okay, so you can have a play about with this. If you click on the battery, you can change the voltage. But I'll just let you pause the video whenever you're wanting to have a go at that and have a wee play about with it. Okay, so I'm just going to talk through some scenarios then. So if we had a fixed resistance, so if we imagine a 2 ohm resistor, just for instance, if we could change the voltage, so increase the voltage, maybe switch out a battery for a more powerful battery, what effect do we think that would have on our current? So that's the last thing to mention there. We've got voltage, resistance, and current. So resistance staying the same, we're having the same opposition to that current, but we're giving it a bigger voltage, so a bigger push, more energy to overcome that resistance. So hopefully it would make sense to you that a larger voltage would result in a larger current. Okay, next scenario, whoops. Okay, next scenario, for a fixed current. Okay, so say we had a circuit that we always wanted to have 5 amps in it. So we want to control that current, we want it to always be 5 amps. But this also got switched out for a larger voltage. So that current's got a bigger push to get around the circuit. But we still want it to be 5 amps. So if the voltage is going to increase, that push for the current is going to increase, then we're going to have to fight it by a kind of equal increase to cancel that out. So for a fixed current, a larger voltage would require a larger resistance. And finally, this one's the one that's a wee bit different. If you've got a fixed voltage, then what would the relationship between current and resistance be? Well, if we had a fixed supply, for instance, a 12-volt supply, if you wanted a small current there, then you would need to have a large resistance to kind of oppose that big drive, that big 12 volts. Okay, vice versa, if you wanted a really large current, then you don't want there to be much fighting it at all. So a larger resistance would result in a smaller current. Okay, so these relationships are actually summed up by this formula here, which is that voltage is equal to current times resistance. And I just want to get into the math a little bit just to kind of prove that the numbers kind of work out there with what we've just said. So bear with me in my touchscreen and my messy handwriting. Come on, there we go. Okay, so first scenario, let's say we've got a constant current. So we want that current value in there to be fixed at 2 amps. Okay, if we had a resistance of 1, so making our value 1 there, then the voltage that would have to go along with that mathematically for this to make sense is 2. 2 is equal to 2 times 1. If we had a larger resistance, so we up that resistance to 2, then we would also need to increase the voltage to kind of combat that increase in resistance. So as the resistance increases, the voltage has to increase at the same rate. And also mathematically, you can see then that both sides of the equation are still going to be balanced because we've increased by the same amount. So I say these two values are directly proportional, which is a phrase I'm sure you've come across in maths as well. Okay, so next scenario, let's keep the resistance constant. Just pick a different number just for fun. So let's say that you have a fixed resistor of 5 ohms. If we want a current of 1 amp, we'd get that with a voltage of 5 volts. If we had a larger current, let's do a big jump now, let's go to 10 amps, then we would need a 10 times larger voltage as well. So same relationship here, increase in the current, increase in the voltage, they're directly proportional. Final scenario, the one that was a wee bit different, is we've got a fixed voltage. So you're using a constant battery that's providing you with 12 volts. And if you have a small current, so let's go for 1 amp, then you would need a very large resistance, which should make sense because we're saying that you need a lot of fight against this push from the battery to give you that small current. If you wanted a larger current, 3 amps, then mathematically a number needs to be 4. So to have a larger current flowing around your circuit should make sense that we need a less resistance to that, so we have a smaller resistor. So that formula, V equals IR, then is showing us the relationship between current, voltage and resistance. The way I could show this one actually with the arrows then, so we're saying that an increase in the current is a decrease in the resistance and vice versa. So those two things are inversely proportional. Okay, just want to show you the graphs, another way of showing this relationship here. Both of these graphs are showing that there is direct proportion between voltage and current. There's an increase in voltage and an increase in current at the same time. Both of them do show that. There's some things that one graph might be more useful for than others. You can see the steepness or the gradient of the line is different in the two. So if I had the same set of results and plotted graphs both ways, they would show the same relationship, plotted all my points correctly, but the gradient would be a wee bit different. So if I just try and explain that for a wee second, so if I pick a point, just for instance, say for this experiment, I got a voltage of 3, provided a current of 2, then that would be a voltage of 3 and a current of 2. So show the same thing, it's just the gradients are going to be different, related but different. Okay, so if we were doing an experiment and we wanted to show this relationship between voltage and current and wanted to analyse our results, which of course what's a graph helps us do, it helps us kind of see a snapshot of this relationship, but it helps us go a wee bit further into the relationship as well, then this graph would actually be the most useful based on what we've just seen about Ohm's law. So from your maths, I know you've come across gradient before, and you know gradient's a measure of the steepness of the line, and you know some formulae to get gradient. You might be thinking y2 minus y1 over x2 minus x1. Really what that's doing is telling you the difference in the y direction compared to the difference in the x direction. You might have first learned gradient is vertical over horizontal or up over along or something like that. So if we look at that first graph that I've circled, then the vertical represents the voltage and horizontal is the current. So the gradient, vertical over horizontal, be vertical is voltage, horizontal is current. And actually, that is a rearrangement of the formula that I've just shown you in the first page. If voltage is equal to resistance times current, then resistance is equal to voltage over current. Why that's useful with a graph is that actually means that if gradient is vertical over horizontal, but vertical over horizontal is voltage over current, then the gradient in this case must be equal to the value of the resistance. So that makes it quite a useful graph for us if we're wanting to analyse our results a wee bit further and say, okay, what's the relationship between voltage and current, but what's the value that connects them, what is actually the resistance of this circuit? So the gradient is the value of the resistance, but that's only the case if your vertical is the voltage and the horizontal is the current. If you had your axes the other way around, you could still get it, but the maths is a wee bit trickier and this is the easiest way to go. Okay. Oops, sorry. Okay, just to point out resistance, as you mentioned in your homework last week, it can also be recorded or measured using an ohmmeter. So as well as having your values for voltage, your values for current, we could plot that graph and we could work out the resistance was the gradient of the line. There is something called an ohmmeter. It's another function in that multimeter that you would use in school, and that would give you a reading for the resistance of the component. It does do what we would need to do the kind of long-winded way as well, though. What it does is passes a current through the resistance, takes measurements, and just does the calculations for us. Okay, final thing to point out in these graphs, like I said earlier, not all components have a constant resistance. For instance, the filament lamp can increase as it heats up. You'll learn about other components as well. Resistance don't stay constant, like a thermistor or a light-dependent resistor, but that's later on in the course. So if a component has a constant resistance, then this graph would look like a straight line with a constant gradient. If its resistance is changing, then the line's not going to be straight because a constant gradient would mean a constant resistance. So if its resistance is increasing, the kind of steepness of our graph is going to increase. So what we end up with, it's going to be very messy, but it's going to increase as we go up. Okay, so if we've got a straight line, it means we've got a constant resistance or a constant gradient. If we're talking about a component that doesn't have a constant resistance, then its graph wouldn't be a straight line. Okay, last thing I want to do then is just see if we can use this formula and solve some problems with it. So the first question I've got here asks for a reading in an ammeter. So from last time, remember that an ammeter measures current. So we're looking for current, and current has the symbol I. What do we know? We know the voltage is 12 volts, and we know the resistor has a value of 5 ohms. The ammeter is placed in this circuit kind of to the left of the resistor, as you see here, but remember, it doesn't matter for this type of circuit where it would be placed. It's that kind of traffic jam analogy. The current is the same at every single point in the circuit, and you can see that from that FET website as well. It wouldn't matter where you take this reading. This 5 ohm resistor is having an effect on the circuit as a whole. So if we want to know the reading in this ammeter, we are looking for current. The formula that would help us answer this is that voltage is equal to current times resistance. Okay, you've got options here. You can either rearrange the formula. So I showed you that earlier when I was making the link with the graph. It's a very useful skill to be able to do. Or you can substitute the numbers in just now and rearrange later on. There's kind of pros and cons to doing both. Some of you will prefer one method over the other. I'm going to substitute in the numbers as they are just now. So voltage is 12. Do you know what? I'll do it both ways. The current is the thing that we don't know, so I'm just going to keep that called I just now. And the resistance is 5. So I've got 12 equals something times 5. 12 equals current times 5. Okay, you might be spotting already how you'd work out that missing value. Something times 5 is 12. How do you work out the something? Or a bit more mathematically, we can think, okay, if I want that I on its own, what's going to happen to this times 5? It's going to change sign, and we're going to get 12 divided by 5 on the other side. So I'm going to have I on one side and 12 divided by 5 on the other. But I'm just going to write it this way. Hopefully you're okay with me missing that step there. Basically, to get I on its own, the 12 has to be divided by 5. Okay, 12 divided by 5 would be 2.4, and current is measured in amps. I'll just do it the other way as well. It'll take too long in this problem, but okay, so say you look at this problem, you go, right, oh, this is an Ohm's law problem. We've got voltage, current, and resistance. Start with this formula. And it's the same formula, but rearranging it, if we wanted to work out what I was, it would be V over R, but that's the same principle, really. Instead of multiplying by the R on this side, and take that across, and it becomes a divide by R on the other side. You might also be aware of the kind of triangle method for rearranging this. V at the top, because it's on its own there, I times R. So if we want I on its own, it becomes V over R. Okay, as I said before, you've got options though. If you prefer my last method, do it that way. Keeping going with this way, we've got I equals 12 over 5, and we get 2.4 amps. Okay, next question. What is the value of the resistor? So if you recognise this symbol from earlier as a variable resistor, so we could set it to different things. We've got a cell this time, providing 3 volts, and we've got a current of 2 amps, and exactly the same as before, it wouldn't matter where that was positioned, because in a simple circuit like this, that traffic jam analogy, the current's going to be the same at every single point. Okay, so the value of the resistor, we're looking for R. do it both ways again. So starting with the formula as it's written in your formula sheet, which is that voltage equals current times resistance. Substituting in what we know, under V the voltage was 3, the current this time we did know was 2, and it's the resistance we're trying to work out. So 3 equals 2 times something. You might already spot the something, or if we wanted the R on its own, then instead of it being multiplied by 2, the 2 would have to come across and we'd have to divide by 2 on the other side. So R would be 3 divided by 2. R would be 1.5 and resistance measured in ohms. Okay, so that's quite messy. The other option, just quickly, so start with the formula as it's given to us, V equals IR. But if we rearrange it, then resistance, and V was top of the triangle, stays on top, V over I. So resistance, we end up in the same place with 3 over 2, which is 1.5 ohms. Okay, last example. What voltage is supplied by the battery? So we've got a symbol for a battery now, remember that's 2 or more cells. And we've got a current of 1 amp and a resistance of 3 ohms. So this one's actually a bit easier because the voltage is the thing that we want. That's the thing at the front of the formula. So no need to rearrange. Substituting, V is the thing that we are looking for. I was given as 1, resistance is 3, and it would be 3 volts. Okay, so you're going to have to go at some problems for us just now. Another thing to kind of watch out for that I haven't got into but that you have done before is whether we're looking at milliamps, kilovolts, and dealing with those prefixes first. But you've done a wee bit of work on that recently, and any problems you can let us know. Okay, so today we have looked at resistance then. Resistance is a measure of the opposition to the current. It's measured in ohms. You can get variable resistors where you can change the value of the resistance, or you can get fixed resistors where it just tells you how many ohms that's providing. We looked at the graphs that show the relationship between voltage and current, and the fact that if it's voltage against current, then the gradient of that graph would be the value of the resistance, and we've had a go at some problems. Okay, see you next time.